Hello class, welcome to our first lesson of Chapter 4. Chapter 4 deals with graphing trigonometric functions. So today what we're going to look at is the 6 basic trig function graphs. A lot of what you're going to do during this set of lessons is to think about how the graphs change. So think like transformations from algebra, for example. That's a lot of what we're going to be looking at as we go through our class. So today I just want to give you some basic info about the graphs and make sure you see how they're set up, and then we'll kind of go from there as we move forward in Chapter 4. Some vocabulary that you want to make sure that you know about. Number one is what's known as the period. The period is how long it takes the pattern to repeat itself of a sine graph or a sine wave or sinusoidal function. Essentially, that's how long does it take horizontally for the graph to repeat, because these graphs will look like sound waves or wavelength. And so most of the graphs that we're going to see will have a period of 360 degrees or 2 pi radians, because one time around the circle is how long it takes to repeat itself. But we'll go through some of those with each graph. The second thing to understand is the amplitude. The amplitude is how high and low the graph goes from equilibrium, though. So if this is middle ground, the question is how high up does it go and how far below equilibrium does it go? Some graphs have an amplitude, others do not, but the idea of amplitude is important on all 6 of the graphs. So today what we're going to look at is a sketch of each graph. We're going to find the period and amplitude and also discuss some things on domain and range. I'll be honest, our discussions probably will go through the period and amplitude more than domain and range will, but all 4 things are helpful to know about when it comes to the trig graphs. The first graph we're going to look at is the graph of y equals sine theta. A lot of times when I write things in my notes, I use sine x. That's irrelevant to the question. Theta is a nice thing to use on a lot of these because that represents the angle. So what we could do is go through all of these points and plot them and connect the dots. I'll just go through a few things. First off, this is where sine is sine of 0. So if I plug in sine of 0, it's 0. Sine of pi over 2 is sine of 90. And that's straight up on the y-axis, and it's 1. And then 180, or pi, is back to 0. 3 pi over 2, or 270, sine of that is negative 1, and then back to 0 at 2 pi. That is the main part of the graph that you want to make sure you understand. The graph keeps going on both ways forever, and it makes this wave back and forth. So I circled the 0 location of the 2 pi to say that's one period of the graph, because it takes that long to get back to start and then repeat. So this graph has a period then of 2 pi, which makes sense because all students take calculus. One time around the circle is how long it takes it to say it's positive, then it's positive, then it's negative, then it's negative. Okay, and those are the ideas that you want to think about when it comes to that situation. The amplitude is how tall the mountain or the hill is from equilibrium. Equilibrium is this line right here, okay, the x-axis. So it goes up 1 from there and down 1 from there, so the amplitude is 1. The domain is what numbers can you plug in. That's everything. The range is what's the lowest to highest numbers. The lowest value you can have is negative 1. The highest value you can have is 1. This is what's known as interval notation if you're not familiar with it. The bracket means it can be that. If it was a parenthesis, it means it couldn't be that. But the range is only from negative 1 to 1. This explains why if you try to do sine inverse of, say, 3, you got a domain error because 3 doesn't exist in the y values for a sine graph. The next graph we're going to look at looks a little strange, and it's known as the cosecant graph. Remember, cosecant is the reciprocal of sine. So the easiest way to graph cosecant is to basically graph sine and then flip everything. So you'll notice here I put kind of a dotted version of the sine graph that's just from the other slide. Okay, so I just remade the sine graph, just made it dotted so you can see a basic idea of it. I'm going to use those dots that I had before at 0, pi over 2 at 1, back at 0 at pi, negative 1 at 3 pi over 2, and back to 0. And then I'm going to take everything and flip it. Well, the important thing is any spot where sine was 0, if you flip it, that makes instead of 0 over 1, it makes it 1 over 0. And that's undefined. And so those spots are all going to be vertical asymptotes because you can't divide by 0. And then any spot that was a maximum highest point or minimum lowest point, essentially what you do is just put a dot there, and then all the numbers are going to flip, which means instead of going this way, they're going to go in the upward direction, and they make what look like parabolas going in the upward and downward directions. Notice the period is still 2 pi because it takes 2 pi to repeat itself. The amplitude is none, but the amplitude per se, in quotations here, is 1. because this would just determine where you start from. So if there was a 2 in front of this, it would go up to 2 and start from there. The domain is x can't equal 0, pi, 2 pi, 3 pi, etc. So basically any integer times pi doesn't work. Notice the range here is the opposite. Okay, I'm writing this a little bit different than what you may have seen in the past. But negative infinity to negative 1 says it can go all the way down as far as you can go and stop at negative 1. And then it starts at 1 and goes up as far as you want to go. Okay, again, the period and amplitude is going to be more vital to your success in Chapter 4 than the domain and range pieces are, but they're still there in case you want them. Now that we've gone through sine and cosecant, cosine and secant should go a little bit faster. The difference with cosine is everything's flip-flop from sine. Okay, so x instead of y over r, I'm using x over r. So the first point is up at 0, 1, because if I'm at 0 degrees, the x value is 1, and so it's 1 over 1, which is 1. And then essentially they're all following the pattern just like sine. It's just kind of shifted over a little bit. And so the next one would be pi over 2. That's at 0. Pi would be at negative 1, 3 pi over 2, and 2 pi. Okay, those ideas are kind of what you're looking at for that situation in order to figure out what the answers are for the cosine graph. The graph is typically from 0 to 2 pi again, so that's why its period is 2 pi. The amplitude, how far up and down do they go from equilibrium? Remember, okay, that's the x-axis, up 1, down 1. And what you'll notice is the domain and range is the same as the sine graph earlier because it's just literally the same graph, just shifted over a little bit. The secant graph is the cosine graph flipped around. So at pi over 2 and 3 pi over 2, cosine was 0, which means if I flip it around, I'm going to have an asymptote at those spots because I can't divide by 0. All the high spots go a parabola upward. All the low spots from that lowest point in the cosine graph make a parabola looking downward, not crossing the asymptotes. So the period is 2 pi here still. The amplitude is none, but really it's a 1. Okay, but there is no highest and lowest point. That's why there's no amplitude. The domain is x can't be the over 2's now, so it can't be pi over 2, 3 pi over 2, 5 pi over 2, etc. And then the range is everything from negative infinity to negative 1, and then from 1 to infinity, just like cosecants. So you notice there's similarities between sine and cosine, sine, cosine, and some similarities between cosecant and secant. So those 4 graphs go together. The odd ones tend to be the tangent and cotangent graphs. Now what you'll notice here about tangent, first off, is that the graph doesn't make this nice sine wave. Okay? It doesn't go up and down, it doesn't have these parabolas. It kind of looks like x to the third. It kind of goes upward in that direction. The period for tangent is pi, not 2 pi, and here's the reasoning. Use all students take calculus. In quadrant 1, it's positive. In quadrant 2, it's negative. In quadrant 3, it's positive. Quadrant 4, it's negative. So it goes positive, negative, positive, negative. Well, it only takes 2 quadrants to repeat. That's why the period is pi, not 2 pi. The graphs go up and down forever. So the range is going to be everything. The amplitude will be none because there's no highest and lowest point here. The domain is everything that can't equal the over 2's. And the reasoning is because tangent by definition is y over x or sine over cosine. So the asymptotes for tangent are wherever the asymptotes for secant would be, or wherever cosine is 0. So cosine is 0 at pi over 2 and 3 pi over 2, 5 pi over 2, etc., which means my tangent graph will have the same asymptotes. Now notice this graph is zoomed in a little bit, and the reason is because I want to be able to show where those numbers are coming from. 0, 0, tangent of 0 is 0. And then notice here at pi over 4, the answer is 1. Because if I plug in pi over 4, that's 45 degrees, and opposite over adjacent, or y over x, are both the same. So these are the guiding points now. So I've got 0 halfway in between. Okay, so notice here's an asymptote and another asymptote. Halfway between is where the 0 is. And then kind of one spot over and one spot back, up and down 1. That's where the amplitude number would come into play. If there was a 4 in front, it would go up 4, down 4. Okay, so those numbers are still important even though there is no set amplitude to the graph.